Hello, hello everyone, and welcome back to Unconventional Computing CS492A in fall 2024. Today we will start chapter 4 about quantum computing. I think quantum computing is still part of unconventional computing, although engineers and physicists work hard to make it practical. Also, this is not a course on quantum computing, but only chapter 4, one of several chapters in this course on unconventional computing. So we will not, by far not be able to cover all aspects of quantum computing, but I promise you it will be an exciting chapter. And so with that, let me start sharing the slides. Yes, here we are. So let's start with an overview of chapter 4 in quantum computing. We will start with some classical physical experiments that kind of required the development of quantum theory. And we will recall the mathematical foundations of quantum mechanics as developed in large part by John von Neumann. In particular, we will need to talk about states and operators, mathematical concepts. Then we will talk about pure states and how they differ from mixed states. We'll talk about entanglement and the Einstein-Podolsky-Rosen thought experiment, which was later actually conducted in practice, confirming that the mathematical foundation of quantum mechanics itself is a quite unusual theory, and also meaning that our physical reality has some very strange properties. Either it's non-local or it's non-deterministic. Then we'll proceed to how to harness these strange effects for efficient computation. We'll talk about qubits. We'll talk about primitive gates of quantum circuits. Then we will see some examples of quantum circuits. And we will close with Peter Shor's famous algorithm for factoring integers. And algorithm is put in quotes here because this is not an algorithm in our traditional sense of CS300 or CS500, but it's actually a special type of quantum circuit. So that's our plan, and this will keep us busy probably today and also for the next sessions. So stay tuned, and now we start with a recap on physical experiments. So I want to first remind you, probably you have learned that electrons are particles. But how can we prove that electrons are particles? You learned that probably from your teacher, from your professor, by just believing, right? But how did physicists arrive at the conclusion that electrons are particles? And there's a famous experiment by Robert Millikan, who received the Nobel Prize in 1923 for this experiment. The famous oil drop experiment conducted in 1909, which then kind of demonstrated proof that electrons are particles, and in particular that electric charge comes in integer multiples. You can have 1 electron charge or 2 electron charge or 3, but not 1.5 electrons value of charge, or not 2.5. And this is a depiction of this famous experiment. In this experiment, there's oil is sprayed into a chamber with air, and the oil particles are very small, and they tend to lose or acquire 1 or 2 or 3 electrons while being blown here through this cover, so that they're charged. On the other hand, they have some weight, right? So that gravity pulls them down, and they enter here this second chamber to which electric field is applied. And so the electric field pushes up the electrons depending on how much charge they have, right? So if they are charged with 1 or 2 or 3 electrons, then the electric field pulls them up, but the gravitation pulls them down. And then Millikan adjusted the strength of the electric field so that the oil drops would float, so that the force, gravitational force pulling them down would be equal to the electric force pulling them up. And in this way, he was able to measure the electric charge of every single oil drop individually, and to observe that this charge comes in multiples of 1.6 times 10 to the minus 19 electron volts. And thus he concluded that electrons only appear in integer multiples, and thus that electrons are particles and not charge does not appear in continuous quantities. So that's a famous experiment. And shortly before, Einstein similarly proved that light is also composed of particles. Now, again, you know that, right? But you only know that because somebody told you, your teacher, your professor. But where's the proof? And that's why made Einstein receive the Nobel Prize. Einstein did not receive the Nobel Prize for relativity theory. Einstein did not receive the Nobel Prize for Brownian motion. Einstein received the Nobel Prize for interpreting an existing experiment, the so-called light electric effect, from which he concluded that light also consists of particles, we nowadays call them photons, and not of continuous quantities. So here's a picture of the experiment, which was not conducted by Einstein, but before, and Einstein only interpreted this experiment. So the experiment proceeds as follows. Here's a vacuum, and there are 2 electric conductors here between the vacuum, and light is shining on one of the conductors. And nowadays interpretation is that the light particles kick out electrons from the surface of this conductor, and the electrons then they have basically no weight, so they start to proceed depending on the initial velocity obtained from the light particles to move through the vacuum. There's no obstacle, no, that's why it's a vacuum, towards the other conductor, and thus there's a current happens, right? And then we can change the parameters of this experiment. We can increase the intensity of the light. And then if we increase the intensity, 2 possible things could happen. If we increase the intensity, then maybe more electrons get knocked out of this conductor, and therefore the current increases. Or if we increase the intensity of the light, then electrons start to get knocked out faster and proceed faster to the other end. And in order to investigate the second case, there's a voltage applied, which actually repels the electrons and pushes them back to where they came from. And the voltage is then manually adjusted such that electrons just barely cannot reach the other conductor anymore. And then we can change the parameter, it can change the intensity, or we can change the color of the light. And it turns out that changing the intensity will not change the current, the voltage required to attenuate, to dampen the arrival of electrons. But when moving the color, changing the color from red towards blue, then electrons start arriving and require the experimenter to increase the voltage so that the electrons don't arrive anymore. So here's the picture of that. Red light, green light, and blue light. And then increasing the intensity, and in this direction, increasing the voltage for stopping the electrons. And for stopping blue electrons requires more voltage to stop them. Requiring green electrons requires less voltage. Requiring stopping red photons requires even less voltage. So that means that the color of the light is essential and not the intensity. And the explanation is that each photon, thus proving that photons are particles, each photon can hit out one electron. So by increasing the intensity does not produce faster electrons, but only produces more electrons, whereas changing the color produces faster electrons. So that's the famous light electric effect, for which Einstein's interpretation got the Nobel Prize. So to summarize, light is consistent of particles and electrons are particles on the one hand. But there are other experiments which suggest kind of the opposite. Namely, 100 years before Einstein and Millikan, Thomas Young proved that light is actually a wave, not a particle. How did Thomas Young prove that? With the famous double slit experiment. So he made two very thin slits, double slit into such a blind, and then shed light onto this. And the expectation was that there would be on the screen, there would be two maxima of light, but turned out there were not two, but many of them, the famous interference pattern. So here you see a modern day reproduction. When there's only one slit, then as we expect, there's a beam of light which passes through that one slit, and left and right, the blind keeps the screen dark. But if we have two slits, then there's this substructure of all these small maxima. And this is because of interference. And interference, as we know, means that there must be waves which interfere. So that means light is a wave, not a particle. And it turns out that the same also applies for electrons. This is another very famous experiment in the 1950s, so relatively young, conducted by a famous German physicist who also, he needed much thinner slits, right? And then they accelerated electrons towards that in vacuum. and they obtained a similar interference pattern, which is strange because right, electrons, there can be only one electron or two, but over time, what happened is that somehow the electrons kept arriving more frequently at some places than at others, so that over time, this the intensity, accumulated intensity, exhibited the same interference pattern, thus suggesting that electrons are also waves. So to conclude, light is composed of particles and it's a wave. Electrons are composed of particles and behaves like a wave. And this paradox kept physicists on their toes trying to explain this seeming disagreement. And quantum physics thus was developed, had to be developed as a way to reconcile these two seemingly opposing observations. So this is, let's now briefly recall the basics of quantum mechanics as was then developed in early 1900 by Erwin Schrödinger, Werner Heisenberg, Paul Dirac, John von Neumann, and others. So these are just some example scientists that helped develop quantum mechanics. And we're in this chapter, we're only going to look at the basic quantum mechanics. We're not going to look at more recent developments, such as the path integral approach promoted by Richard Feynman. We're not going to look at quantum field theory developed by Dyson, Feynman, Schwimmer, Tomonaga, and others. And we're not going to look into relativistic quantum mechanics, which is an entire can of worms of its own. So only the basics for now, because we're aiming at quantum computing. It's just one chapter in this entire course. But I understand that there are dedicated courses on quantum mechanics in the physics department and also dedicated entire courses on quantum computing, maybe in double E. Anyway, so let's look at basic quantum mechanics as was developed by John von Neumann and others. And I'm particularly referring here and promoting this book, Mathematical Foundations of Quantum Mechanics by von Neumann. So let's look at the general picture of a physical theory. A physical theory is something which connects physics to mathematics. Mathematics as a way of describing physics. Mathematics is the language of physics. So, and here we're going to look at 5 axioms, which I will elaborate further. But let's start with a survey of these axioms. So on the one hand, we have physics, and on the other hand, we have mathematics describing the physics. And different parts of mathematics are used to describe different aspects of quantum physics here in this case. The next slide will explain similarly the relation between mathematics and Newton physics, which is much easier. That's one of the reasons why quantum physics is so hard to grasp. So what aspects of a quantum system can we describe mathematics? First, we're going to consider to fix a quantum system. Technically, it's supposed to be an isolated system, not interacting with another. If it is interacting with another system, then we need to include the other system and thus considering the compound system, which then is isolated. If that in turn interacts with another, then we need to include that as well until we've finally arrived at an isolated system. Here's an example. There's an atom with, this is supposed to be an atom with its core and with some electron bands around it. And the mathematical foundation of quantum mechanics says, in order to describe such a physical system, mathematical formalism is a Hilbert space. You can learn about Hilbert spaces in math department lecture on maybe functional analysis. Maybe finite dimensional or infinite dimensional. For all purposes, for computing purposes, we will focus on finite dimensional Hilbert spaces. Then we want to observe this system. So now we consider some observables. Such an observable could, for example, be the energy of this atom, or it could be the momentum of this atom, or the velocity, or the position. These are typical observables of such a systems. And the mathematical description, according to von Neumann, of these observables are, so here is a picture of an observable, one observable, maybe the x-coordinate of this atom. Here's another observable, A prime, which could be maybe the y-coordinate of this atom in some trap, ion trap. So two example observables, and mathematically, Neumann says these correspond to Hermitian operators. So Hermitian is basically means symmetric or self-adjoint in the complex case. Again, you can learn about Hermitian operators in functional analysis. In the finite dimensional case, it just means a matrix which is whose transpose and complex conjugate recovers the original matrix. So that's the correspondence between physical observables on the one hand and the mathematical description in quantum mechanics on the other hand. Next, we want to talk about states. First, we focus on pure states. So this system might be in some state, including might have a certain position, x and y position, could have a certain energy, could have a certain momentum, velocity, x or y velocity. These are all captured by the states physically. And according to von Neumann, the mathematical description of these states are unit vectors so these are two different states of the same system. And according to von Neumann, the mathematical formalism for describing these states are normal vectors in the Hilbert space that we had fixed for the system. So this is still the same system, right? But in two different states. And therefore, it's described by two different normal vectors. Normal means vectors of length 1 length in the Hilbert space. Okay, moving on. These are already the first 3 axioms, quantum mechanics. Let's now talk about measurements. So that's an important, subtle but important distinction. Observable means something we can observe, but only when we perform a measurement, then we do observe. This is something that already Einstein emphasized when he concluded about the relativity of time. We can not talk about the time of a maybe distant object unless we measure the time, and that's where the time dilation happens. And similarly, in quantum mechanics, only when we observe the position, then we make a measurement. This is, like Schrödinger's cat. If we don't observe Schrödinger's cat, then we cannot know whether it's dead or alive. So performing a measurement of the observable A or A prime on the system in the state S or S prime corresponds to, according to von Neumann, to, the result of such a measurement will be an eigenvalue A of this operator. So you know about eigenvalues from linear algebra in the finite dimensional case, and in the infinite dimensional case, as usual, things become much more difficult and subtle. But anyway, we're going to focus on the finite dimensional case. So you see here, performing a measurement is indicated here with the eye blinking, and then the result will be an eigenvalue. And in general, such an Hermitian operator or symmetric matrix can have many eigenvalues. And one of the particularities of quantum mechanics is it does not predict which eigenvalue will be the result of the measurement. There's going to be an intrinsic probability, which we will talk about soon, 2 slides in. Now, that's already 4 axiom, and the final 5th axiom is about the time evolution. How does such a system evolve over time? Right? So if we keep this isolated system, maybe it initially had some initial velocity, then classically it will continue with this velocity. And mathematically, according to von Neumann, so right, this is the evolution of the system. The evolution of the system, namely the normal vector psi, is described by Schrödinger's equation, which is a partial differential equation with an imaginary constant I, h bar, and then here's the time derivative. So this is a differential equation. 5th axiom, this differential equation describes the evolution. And this might be all very overwhelming to you because there are two things new for you maybe. The first is this is about quantum mechanics, which is complicated, but also the formalism of physical theory as a relation, a translation, a dictionary between physical aspects like systems, states, observable measurement, evolution on the one hand, and on the other hand, it's mathematical translation, as Hilbert space, normal vectors, and so on. This is also probably something you had to have not seen before, but well, at least not implicitly. Probably you have seen these correspondences for other physical theories, such as for Newton mechanics. So you all know about Newton mechanics, describing, for example, the motion of the planets in our solar systems. So just to illustrate that Newton mechanics is also of such a form or translation between physics and mathematics, only the mathematics in Newton mechanics is much simpler. So this is a brief detour of how Newton mechanics translates between physics and mathematics. So let's consider here our solar system, right, as a special type of isolated system. Isolated means I'm going to ignore any asteroids passing through the system. And then it's an isolated system. And how is it described mathematically? Well, it's described by the positions and velocities of each of the planets. Okay? So let small p denote the number of planets, 9 or 8, depending on how you consider Pluto. And each planet has 3 Euclidean coordinates for the position x, y, and z. And it has 3 coordinates for its momentum, for its velocity, x velocity, y velocity, z velocity. So 6 degrees of freedom for each planet and p planets, so that the whole system in phase space is 6p dimensional, right? So here's the Earth. Next is Mars, Jupiter, Saturn, and the next one I keep forgetting. What's the next after Mars, Jupiter, and Saturn? Anyway, let's move on. So after describing the system in this simple Euclidean, high-dimensional Euclidean space, what is the state? The state of such a system is simply one vector in this phase space, right? So a 6p dimensional vector. And if we have 2 different states, maybe in one state, state keeps changing all the time, as in this picture, right? So in one state it's u, and in another state it's u prime. What are observable? Observable are the positions and the velocities of each planet, and these are described by projections. Take such a 6p dimensional vector and project it maybe on the first coordinate, that would be the x coordinate of the first planet, Mercury maybe. Next, projection on the y coordinate of the first planet, then projection on the z coordinate of the first planet, projection on the x velocity of the first planet, and so on, and then proceeding to the next. So all these are observables, position and velocity of each planet, and these mathematically correspond to projections. Take a state vector and just look at one particular component. Measurement, and that's what makes Newton mechanics so much simpler than quantum mechanics. It's just the result of the value of such a projection. Projection returns measuring the position of a planet or the velocity of a planet. And time evolution, how does such a system evolve over time? This is exactly what the Newton's law and Newton's equation describe, right? Newton's law of gravitation, it describes the force exerted by the sun and by the other planets on, for example, the Earth. And Newton's equation, second order differential equation, states how that force affects the velocity and the position of the Earth, and similarly for the other planets. So it's same type of correspondence, and basically every physical theory of this form is of this form. But here we want to focus on quantum mechanics. So we talked about how light behaves both as a particle and as a wave. We saw that also electrons can behave both as a wave and as particle, and silver atoms can behave as particles and as waves. Magnesium ions can behave as particles and as wave. And this kind of schizophrenic behavior that is exhibited in experiments can be described using the formalism of quantum mechanics as described by John von Neumann with these 5 axioms. Some of these axioms have sub-items, such as, for example, pure and mixed states, and the result of a measurement and the state after measurement. That's two essential aspects of quantum mechanics, is that the result of a measurement is non-deterministic. There's a probability associated, and every measurement affects the state, which is not necessarily true when we make classical measurements. For example, the position of a planet, measuring the position of a planet does not really change the position of a planet. And this is where we continue next time, talking about how we can harness these strange effects for accelerating classical computation using quantum gates and using quantum circuits.